Hello, everyone. I'm Yubin Dai from Zhejiang University, supervised by Yuan Chaoshu. It's my honor to be here to introduce our work, AI mapping, edge-assist real-time depth mapping with low bandwidth requirements. It's noted that AI it's just edge-assist real-time for short. It doesn't use audio information, and we do our task using camera devices. Okay, let's go ahead. At the beginning, I will introduce 3D reconstruction and its common applications in daily life. Depth mapping, or 3D reconstruction, models the environment in real time using camera data, which is essential for applications like AR and autonomous driving. It enables accurate environmental reconstruction, supporting latency-sensitive tasks such as path planning and optical avoidance for autonomous driving in dynamic environment. Real-time 3D reconstruction is crucial for these applications, as it ensures effective and reliable system performance with minimal latency. 3D reconstruction methods use either explicit or implicit representations to represent surrounding environments. Explicit representation methods such as voxel, point clouds, meshes, it uses explicit data structure to store the scene information. However, this will generate a lot of memory cost for high-quality reconstruction as the reconstructed scene get bigger. For example, the paper on the CVPR Octanight learned deep 3D representations at high resolutions. It results in a memory usage of 17 GB when reconstructing a modern night dataset as a resolution of 256. To mitigate memory usage while maintaining good performance of generating new win points, implicit representation techniques, NERF, have been introduced. Its basic idea is to train the neural network with scene information and store the information in the network. These methods typically yield high-quality reconstruction with low memory cost. However, the approach also has its downsides. First, training neural network for implicit representations is computationally intensive. And the second, it is also difficult to locate spot data region in the environment because it stores the information in the network. Due to the limited computational resources on mobile devices, current implicit neural representations are often implemented within an edge assist framework. So, how to design a system for it? For edge assist framework in implicit neural representation system, there are several challenges to be addressed for this question. Firstly, from the data perspective, how to quickly identify and sample valuable data on the mobile side. 3D reconstruction involves iterating between sampling new areas from previously unobserved areas within the environment and scene representation. Explicit sampling, such as predicate sampling or welfare overlap-based sampling, are simple heuristic rules that struggle to locate the spot data regions. Other sampling methods that rely on implicit surface analysis can accurately locate the spot data regions, but encounter issues with low latency. Secondly, from the computation resource perspective, how to effectively utilize the computation resources on the edge side for data processing. Thirdly, from the communication perspective, how to minimize communication overhead in a mobile edge environment while still maintaining reconstruction performance. So, there are several programs used in 3D reconstruction. Use predefined method to collect data for representation as shown in A, B. Using surface performing method for collect data as shown in C. And we start to think if we could combine this method for data collection. We present a benchmarking table showing the latency required for both representation and surface performing across different devices. It's evident that on all devices, the time taken for one round of the surface profiling process exceeds that of one round of implicit representation by more than 2 times. This presents an opportunity to incorporate explicit sampling during the surface profiling process. As shown in the figure, when sampling little data samples, there is no clear difference in the coverage rate between the explicit and implicit methods. However, the implicit profiling module requires near 120 data samples to achieve a coverage rate of 96%, while the explicit methods require over 200 data samples for similar performance. This demonstrates that implicit profiling can effectively identify high-value data, resulting in greater sample efficiency. After sampling, data is sent to the edge server for further nerve training. We record the data buffer on both the mobile device and the edge and use different explicit sampling modes above. The data flow is mainly blocked on the edge. The data buffer at the edge side provides us with a queue to propertize the transmission and the processing of high-value data for reconstruction. What's more, there is an opportunity for retraining improvement. After determining the new data sent to the edge devices in this round, due to the forgiveness of implicit representation, some selected data from the historical dataset are combined with new data as input for training the network. This makes it worthy to consider prioritizing which data to select for retraining to ensure effective utilization of computation resources. So, we designed an edge-assist nervous system for mobiles, air mapping. It contains 2 parts, mobile sites and edge server sites. Mobile sites use depth camera and NUC to collect scene information and pre-process, and the edge server to have complex natural representation. And the 2 sites are connected with mobile wireless network. In system design, we have 3 main modules. We use hybrid sampling modules on the mobile side to effectively collect camera data for deep process. Use value-based representation module on the server side to efficiently utilize the computation resource with the received data, and use ROI-based data transmission to avoid redundant data transmission. For details, in the keyframe selection part, we first map the depth image into 3D space by applying a coordinate transmission of camera's pose. After this, we discretize the point clouds into 3D voxel space based on a specific voxel grid size. We consider whether we can select a frame as a keyframe for processing based on whether the population of the voxels in the current frame that are not present in the historical map exceeds a certain threshold. After that, we use quick implicit surface profiling to supplement low quality region based on new processed result, and find suitable data in historical data for supplement based on direction check, position check, and max coverage selection. After keyframe selection and low quality region firming, in the ROI-based data transmission part, we obtain a series of datasets to be sent to the edge, including depth, color images, and the corresponding poses with tense tables. We use voxel information and sparse data regions to mask the selected keyframes for ROI-based transmission. For value-based representation module part, first we use value-based ranking. Unlike the traditional first sample, first transmit, first approaches, we try to prioritize sending data groups with higher reconstruction value and evaluate each data group's value. For different sources of hybrid sampling data in the front end, the value is defined as described above. And for optimized frame organization, our workflows will be repeatedly covered multiple times to select the optimized frame for each training iteration. We struggle to choose those high workflows for one addition training round. The algorithm is showing algorithm 1 above. After each optimization round, the loss normalized to each workflow. Workflows with losses exceed the average are marked as unoptimized, thereby increasing the proportion of training focused on under-converged workflows. For evaluation, two baselines are used: critical sampling and repetition, a sampling method that samples days with a fixed time interval for scene repetition. H2 mapping, we use keyframe stamping strategy that samples dates based on the field overlap ratio between two keyframes. We use the common dataset, replica dataset, and the ScanNet dataset in 3D reconstruction. For evaluation, two baselines are used. Oh, sorry. We did module application studies for each module. For A, we compare our method with baseline and can see that our module achieves 90% coverage with minimal number of frames. For B, we can achieve a faster performance improvement through the value-based method. And for C, we compare several commonly used methods for organizing past frame for training. It can be seen that while training on the same number of frames, our method requires less training time while maintaining comparable PSNR performance. And finally, we compare three ROI methods, and it demonstrates that our method can minimize bandwidth usage to the greatest extent. After that, we did some experiments to validate its overall performance. We used different configurations in different modes. First, we prototyped high coverage rate in high bandwidth environment. From figure A, we can know that the time required by the baselines to reach 98% coverage is all near 1.2 times that of our system. It can also be observed from figure D that our system can reduce 3.5 times maximal bandwidth consumption compared to the baselines. And for B, we restricted the bandwidth conditions to 2 MB per second. The result highlights a significant improvement in latency, with our system's latency being reduced by up to 1.7 times compared to other systems. For D, we prototype low latency and record the coverage and PSNR variation. It can be seen that our system achieves high coverage performance. In terms of PSNR, we can see that our system experiences only a slight decrease. When the RY module is removed, our system's PSNR is slightly higher than the baseline, which indicates that the small drop is due to the RY-based transmission. We believe that this trade-off is worthwhile for the sake of reducing bandwidth. We did some experiments in our lab to further validate our system efficiency. For convenience, we set up a low latency baseline in the row system, which is a mode that samples after process. We can see that whether under low latency, normal conditions, or low bandwidth, our system achieves higher coverage compared to the baseline. From the visualization, it's clear that our system achieves better scene coverage compared to other baselines. Our system demonstrates the feasibility of edge-assisted dense mapping and reveals several promising areas for future research. First, robustness remains a key challenge, prompting the need for adaptive modules that can dynamically respond to verify network and resource conditions while maintaining optimal performance. Second, task affording needs deeper exploration, since dense mapping depends on high-quality localization. Developing combined offloading strategy for both tasks within a mobile edge assist framework is essential. Finally, extending 3D reconstruction for richer scene understanding stands out as a particularly exciting direction. In conclusion, we introduced AR mapping, an edge-assisted 3D reconstruction system that features faster reconstruction, high coverage rate, and low bandwidth usage. In its design, we first explore the opportunity to efficiently sample data from the data stream on the mobile side. Then, we prototype the reconstruction process with selected high-value data as well as historical data. In order to reduce the bandwidth consumption, we further develop ROI-based data transmission designed for 3D data samples. We prototype AR mapping with a mobile edge system and validate its real-time performance in various scenarios with different requirements. And if you have any questions, please feel free to contact us by email. Our email address is given below. Thank you. Welcome for question.
Thank you so much. Let's thank the speaker for the presentation. And as it says, there's always questions from the audience, please.
Okay. Hello, this is a very interesting work, and what I'm interested in is about your future work, and you said is you will start to density map and the location. So what I want to know is what is the challenge to put the density mapping and the localization in the mobile edge systems. And so we all know the communication is a limitation. So how about the possibility?
Thank you for your question. I think localization is because if you want to build a good performance of the indoor scene, it needs a good localization and a good dense mapping. So if you only focus on dense mapping, it's lost the location. So I think there is a trade-off between localization and dense mapping. So this is the direction we will work. Thank you.
Okay, thank you.
Thank you so much for your question. Are there any other questions from the audience? Then maybe I have one short question. Did you consider also the energy consumption of your system?
Energy? Yeah.
Yes.
Oh, okay. Thank you for your question. Maybe I think it's a good question because computation and transmission also need they also need energy. Yeah. And we think maybe in the future we can in more base direction to think the direction. Yeah.
Thank you so much. Thank you. Let's thank the speaker once more. Let's give a clap. Thank you.